For centuries, we've been taught that the universe's biggest secrets are hidden light years away in distant galaxies or deep inside the tiniest particles. But what if the biggest mystery of all is the empty space right in front of us? Today, we're diving into a really radical new theory, one that claims to unify everything we see by completely rethinking what nothing actually is. So let's start with a provocative question. Are our best theories of reality broken? Now that sounds super dramatic, I know, but it's a question that physicists are genuinely wrestling with. We've got two theories that are just spectacularly good at describing the universe, but when you look under the hood, you start to see these deep, fundamental cracks. So let's take a closer look at those cracks. I mean, on one hand, our current physics is amazing. It can predict the motion of planets and the behavior of quarks with stunning accuracy. And yet, underneath all that success, there's this really deep and troubling problem where our best ideas just don't get along. It's like this. We have general relativity, which is the absolute champion of the big stuff. Planets, stars, galaxies, you name it. It says spacetime is this dynamic, geometric fabric. Then we have quantum mechanics, the undisputed master of the tiny world of particles and forces. It basically assumes space is just a boring, empty stage for the action. The problem? If you try to use them together, like to describe what's happening inside a black hole, the math just implodes. They're written in two different languages. And this conflict leads to some seriously weird puzzles that keep physicists up at night. Like, why do particles have the specific masses they do? They seem totally random. Or, how does a fuzzy quantum maybe suddenly snap into a definite this is what happened? And get this, why does a neutron seem to live for a different amount of time depending on how you measure it? These aren't just little details, they are huge holes in our understanding. Okay, so this brings us to a really fascinating potential solution. It's called dynamic vacuum field theory, or DVFT for short. And it kicks off with a simple but absolutely mind-bending idea. What if empty space was never the background? What if it's been the main character all along? The heart of DVFT is this. The vacuum isn't nothing. It's a real, physical, dynamic thing, a field that fills every single nook and cranny of the universe. And in this picture, everything we see and experience, space-time, gravity, you, me, the particles we're made of, it's all just different kinds of ripples in this one single fundamental field. So how can one field do all of that? Well, it has two key properties. The easiest way to think about it is like the skin of a drum. The field's amplitude, or its density, is like how high or low the drum skin is. Denser spots create more gravity. Simple. Meanwhile, its phase, or its coherence, is like the vibration of the drum skin. And that's what creates all the weirdness of quantum mechanics. So you see, gravity and quantum physics, they're just two different things the same field can do. Now, that is a beautiful idea, but a theory is only as good as the problems it can solve, right? It needs to make predictions. So let's put it to the test. Let's see how DVFT handles three of those really baffling mysteries we talked about. Okay, first up, the strange case of the shape-shifting neutron. A neutron that's floating free on its own is unstable, and it decays. The big question is, how long does that take? And the really weird part is, the answer seems to depend entirely on how you ask the question. You see, scientists have two main ways of doing this. There's the beam method, where they basically watch a stream of neutrons fly by and count the decays. That gives them a lifetime of about 888 seconds. But then there's the bottle method, where they literally trap neutrons in a physical bottle and just wait to see how many are left. And that method gives them a lifetime of about 879 seconds. That's a 9-second difference. Now, to us, 9 seconds is nothing. But in particle physics, that is an eternity. It's a huge problem, and the standard model has absolutely no explanation for it. It says there should be one answer, period. So what in the world is going on? Well, DVFT has a surprisingly simple physical explanation. It says the walls of the bottle aren't just a passive container. They actually interact with the vacuum field inside, making it just a little bit different. And that tiny change in the local vacuum makes it a little bit easier for the neutron to decay, shortening its life by, you guessed it, about 9 seconds. The experiment itself is changing the space it's happening in. So that neutron puzzle hints that the local environment can affect quantum events. And that leads us right into our second puzzle, which is all about the famous Schrodinger's cat. We know tiny particles can be in two places at once, so why can't big things? Why don't we see that weirdness in our everyday world? I mean, really think about it. Why can a single atom be in a quantum superposition, here and there at the same time, but a cat can't, or a bowling ball, or a planet? Standard quantum theory is kind of fuzzy on this. It basically says the bigger something gets, the more the environment messes with it, and the quantum effects just fade away. But it never says where that line is. There's no hard limit. But DVFT does. It makes a really clear prediction. It says that as an object gets more massive, its own gravity messes with the vacuum field around it. And at a certain point, that disturbance gets so big that a quantum superposition just can't be maintained. It collapses. And the theory predicts that limit is somewhere around 10 to 100 million atomic mass units, which, get this, lines up perfectly with what we've actually observed in experiments. The standard model, on the other hand, no limit at all. All right, this final puzzle is maybe the coolest one of all. It involves a bizarrely precise mathematical relationship between the masses of three sister particles, the electron, the muon, and the tau. It's a pattern so weird and unexpected that it feels like some kind of cosmic cheat code. Check this out. It's called the Koide formula. If you take the measured masses of the electron, the muon, and the tau and plug them into this weird equation, the answer comes out to 0.666, almost exactly 2/3. Now, according to the standard model, where particle masses are basically random inputs, this should not happen. It is treated as a complete and utter coincidence. But in DVFT, it is not a coincidence. It is a consequence. This theory says those three particles are just the three most stable ways the vacuum field can vibrate. And like 3 points spaced evenly on a circle, they are geometrically locked into place, exactly 120 degrees apart. And if you do the math on that specific geometric arrangement, the answer has to be 2/3. It's not a magic number, it's just geometry. So, when you put these three solutions together, they start to paint a really compelling picture. The neutron, the size limit, the magic number. If this theory actually holds up, it isn't just a small correction. It is a fundamentally new map of the entire universe. The shift in thinking here would be huge. We'd go from a universe where the vacuum is just an empty, passive stage, to a universe where the vacuum is the main actor, the source of everything. We'd go from a set of seemingly arbitrary rules to rules that emerge naturally from the geometry of space itself. And, maybe most importantly, we'd go from two amazing but incompatible theories to one single, unified picture of reality. Now, let's be totally clear here. This is a brand new idea. It is speculative, and while it offers some really elegant explanations for these puzzles, it has to be put through the ringer. It needs to be tested and challenged by the whole physics community. Future experiments will tell us if this is the right path or if it's back to the drawing board. But it leaves us with this one final, fascinating thought. For centuries, we have looked up to the stars and down into the atom for answers. What if we've been looking in the wrong places? This theory suggests that the vacuum isn't the absence of things, it's the substance of everything. And if that turns out to be true, it would mean that nothing is actually the most important thing in the entire universe.